on going forward. Need your batteries, do you think? Just use the finger. Oh, over here. Oh, okay. Screen. Aha, there we go. Perfect. Yeah, perfect. Yeah. Yeah. Banu, shall I wait or start? Wait or start? Shall I start or wait? Start? Okay. So again, welcome everybody. I hope everybody can hear me plainly. So in this last of the three talks, I want to revisit the coupled cluster method for spin lattice problems, but to do it today on a much more complex model. Complex in the sense of difficult to solve, not complex, as you will see, in terms of the Hamiltonian. So the outline is as follows. I'll give you the example of a J1, J2 model on a square lattice monolayer. I'll recap, but this time I think very quickly, the coupled cluster method, because I've done that twice already. I'll come to the results on the square lattice monolayer. I'll tell you why this is an extraordinarily challenging problem. And then to shed light on that, perhaps somewhat obscurely, I will complicate the problem by going to look at the same problem on a bilayer. But the reasons for doing that will be that it will enlarge my phase space, and we will try to come back to the monolayer later and see why, try to give some indications of why it is a complex problem. And then I'll discuss the results. And if I get any time, and I'm not sure whether I will, I will try to say briefly at the end, what are the real deep reasons why this method is so successful? So let's look at a J1, J2 model. It's very, very simple. Heisenberg bonds, J1 on nearest neighbors. That's the single brackets here. Double brackets mean next nearest neighbors. Okay, so here's the picture. The solid lines are J1 bonds. The dashed lines are J2 bonds. We'd like to do this, the most quantum case, spin half. Now, why is this problem complicated? It's complicated for a number of reasons. Even when J2 is not 0, so even for the case of a pure nearest neighbor model, this model is not exactly soluble. Okay. And furthermore, when J1 and J2 are both acting, let's make them both positive. So classically, if J1 and J2 are positive, what the terms would like to do is to make the terms in each of them antiparallel, right? That's classical. So that minimizes the energy. But if I have both of them acting together, you can't do that because J1 wants to make the black and the white squares anti-parallel, but J2 wants to make the black squares and the white squares anti-parallel, and you can't do both at the same time. You're frustrated. That's the meaning of this word. Limiting cases, if J2 is 0, we've got a Heisenberg antiferromagnet, HAF, on a square lattice. If J1 is 0, you've actually got two uncoupled on the non-overlapping 2D square lattices, because the black squares on the checkerboard do not talk to the white squares, and so each of those are independent. For J1 positive, let's ask what happens. Well, when J1 is equal to 0, we have, at least classically, we have this pure Néel antiferromagnet, nearest neighbors anti-parallel. And what you expect is that as J2 increases, and I'm calling this ratio of J2 upon J1 kappa, because again, there's only, J1 just sets the scale of the Hamiltonian, just sets the energy scale, and the only relevant parameter is the ratio of these two things. And at a certain value, and we will see what that value is, this other state sets in, which is the one that the J2 by itself would like to promote. And let's have a look. So when kappa goes to 0, when J2 goes to 0, the ground state phase is a Néel state. It's got, shown with the green arrows here, are the spins, up, down, along every row and every column. Classically, dead easy to see that the ground state energy of this is as shown here. The J1 has got the negative term, but the J2, because the spins are parallel, has got the positive term. The converse, when kappa goes to infinity, or when J1 goes to 0, what happens is that the spins on the blue squares want to be anti-parallel, and the ones on the red squares want to be anti-parallel. These guys don't talk to each other, so they can be aligned with respect to each other. I've put an angle alpha between the, theta, between the spins on the blue and the spins on the red. And it's very easy to see that in that case, the J1 bonds do not contribute at all. Take the square in the middle. It's got, I shouldn't touch this, should I? It's got 4 nearest neighbor reds. These guys, this guy and this guy are at an angle theta with respect to each other. This guy and this guy are at an angle pi minus theta, and the cosine of theta plus the cosine of pi minus theta is equal to 0. Right, so the J1 bonds do not contribute in this case, and so it couldn't be simpler. This is the two classical energies, independent of theta. Quantum fluctuations, it's relatively well known. Thermal or quantum fluctuations actually favor collinear configurations over non-collinear configurations. Classically, that set with arbitrary theta are all degenerate. The moment you put on the slightest bit of perturbation, it chooses theta equals 0 or theta equals pi. And when theta is equal to 0, you see that the spins line up in columns, and when theta is equal to pi, they line up in rows. These are called striped states. It's also an antiferromagnet because there are as many up spins as down spins, but it's a different sort to the Néel. So these are called striped states, either row or column. Where does the phase transition occur? Well, it occurs when these two energies cross. And that's a pretty easy equation to solve. That's kappa equals a half. So classically, this is a very straightforward problem. But as I say, even after now more than 30 years of very intense investigation, there are hundreds if not thousands of papers written on just this model, doing it by all sorts of different methodologies. And even now, there is not a complete consensus on what the phase diagram for this guy is, and we'll come back to that. It's a tough problem. It's a prototypical problem because it's one of the most studied, and it is, in some sense, as simple a frustrated problem as you can get. This class of problems is highly, highly non-trivial. Okay, that's the guy that we're going to start with. Coupled cluster method. Now let me go over relatively fast because I've done this twice. You've seen these transparencies. You've seen that the method is very well applied in a variety of places, as I told you, and showed you some of these examples on Monday. And here's again, the outline of the method. The ket state is written with regard to some model state as an exponentiated creation operator. The bits of S are decomposed in terms of this set of many-body creation operators, but the important point to realize is that all of these bits, all of these multi-configurational creation operators commute between themselves, okay? Similarly, the bra state is written in this seemingly rather asymmetric fashion. I don't like taking the Hermitian conjugate of this and writing this as bra phi e to the s dagger for reasons that I've explained in some laborious detail by now. Instead, I like e to the minus s, but it's not correct, so I put another operator in front to make it correct. The model state is in some sense a generalized vacuum state such that when I let these operators act on the model state, I fill the whole Hilbert space. So I can expand an arbitrary ket state in terms of this complete set of wave functions in my Hilbert space. Now let's come back to the example at hand. You might ask, do such states and do such sets of operators mathematically, if you're mathematically inclined, the terminology is that the state phi is a cyclic vector with respect to a complete set of creation, mutually commuting creation operators. But you need both. You need the state and the operators that act on them. I showed you for a closed shell nucleus or a closed shell atom that such states did exist. It was the field Fermi C and then particle hole excitations on top of it. What about here? Now, what I would like to do is to have one or other of these classical states, the Néel state or the striped antiferromagnet, as my model state. And I say I can do that. What I'm going to do, because what we want to do is to make and we have made a universal program that can be applied to all of these problems. And I don't want to do a different program for every model state. But we don't have to. There's a very simple trick that you can do. And the trick is I will choose my model state such that for example, the Néel state is ups and downs. I would like to choose my reference axes, my spin axes, on each site separately. That's just a rotation, a passive rotation. Passive rotations do not change the SU2 algebra. So it's just a choice of coordinates. But I choose my coordinates locally so that all of the spins are pointing down. They're not really pointing down, but in that set of coordinates, they're pointing down. Okay, so in other words, for the Néel state, the ones that are already pointing down, I keep the spins in such that the z-axis is pointing up. The ones that are pointing up, I choose the z-axis so that it's pointing down. Just a choice of spin states, spin axes. And then the products of spin raising operators are these guys, and by definition, they all commute between themselves. So that's what we're going to do. And I can do this for any classical state. Obviously, when I have chosen the state and done these rotations, I have to re-express the Hamiltonian in terms of the new sets of axes. But that's easy to do. Okay. Just as before, we minimize the expectation value of the Hamiltonian in terms of the sets of C numbers that we are putting in. That gives me essentially the ground state Schrödinger equations for the ket and the bra written in this CCM form. For these guys, it's just because S tilde doesn't appear here. This is a coupled set of nonlinear equations for the S coefficients, for the creation coefficients. And this guy, because S tilde only appears linearly, is a coupled set of linear equations once the S's are known. So you solve for the S coefficients here, you plug them in here, and you solve for the S tildes. Again, I say again, if anybody has a question, don't store it to the end. Please feel free to shout out. Nested commutator expansion for this guy. I showed you last time how it terminates. It terminates again for this model exactly the same way. And again, a reminder, the coupled cluster method satisfies not just in the exact framework where you don't throw away any of these configuration indices I, but you choose some, and that's the only approximation we're going to make, is we're going to choose a set of configurations to keep. But at every level, you automatically start with the infinite lattice limit, by contrast to virtually every other method where you have to start with a finite lattice and let it grow to infinity. We start with an infinite lattice. And at every level of approximation, we satisfy both the Goldstone link cluster theorem, that tells me that the energy scales properly with particle number, and the Hellman-Feynman theorem, which tells me that if I calculate any ground state properties, like order parameters, it will be fully consistent with what I have done for the Hamiltonian. So that's a once over again very quickly, but hopefully you remember all of this stuff from the 2 previous lectures. And if you don't, now's the time to ask. Yeah.
This case, how to get the
I'll come to it. I'll come to it because now I've got to tell you how I make approximations, and that's where this will come. But in a nutshell, before I tell you that, again, if I keep in S a certain number n of these configuration indices I, this is n equations, because for each value of I, there's a separate equation. So there's n equations in n unknowns, but they're nonlinear, highly nonlinear because of the exponent. I solve those. There's no guarantee that there will be a solution or it will be a unique solution, right? But we'll see that that's always what happens. Then I take these, I plug them in here. This is much simpler. This is just now, again, for every value of I, there's another one of these equations. So there's n linear equations in n linear unknowns, and I solve for these guys. So the only thing I have to tell you now is, how do I choose this set of I configurations? And that's what I do now. So Landau sort of expresses everything perfectly. And his first pearl of wisdom here is, the most important part of doing physics is the knowledge of approximation, Right? That's always the key to doing a successful calculation. Now, the only approximation we make is to truncate this set of indices. And remember what this guy is now. It's just flipping a spin from the model state. It was either up or it was down, and you flip it to what it wasn't. And you do it on m of those sites. And ultimately, you'd like m goes to infinity. But I can't do that, right? So what do? I use this so-called localized sub-m scheme where on the lattice, I carve out all possible numbers of m spin configurations where every site in that configuration is nearest neighbor to at least one other. Okay, so it's as I drew it here. Suppose we were doing L sub 4. 4 spins in a row is obviously a compact local. So is 4 on a square. So are these configurations, etc., etc. And you have to do this in such a way that you don't want to count too many. This 4 in a row here is the same as 4 up here because we've got rotational symmetry. This guy is the same as this guy because we've got reflection symmetry. So you take into account all of the point group symmetries to minimize that number. And at level m, you take what you get from that. So you carve out all of these size m in graph theory language lattice animals. You populate them with wrong spins in all possible ways, and you solve the derive and solve the equations at that level. So you start out with, in this case, we've got a conservation law here. We know that our ground state is in the total z component of spin is equal to 0. And so when I start flipping spins, it's silly of me to go outside that sector, because these sectors, which are determined by the quantum number, the total z number of spin, is a conserved quantity. It commutes with the Hamiltonian, easy to see. So each of these sectors is disjoint from the other. So use whatever symmetries or conservation laws that you've got. So for example, I would not include this one because this is these sites, this one, and this one are on, let's call them odd sites, and this one is on an even. And so when you flip there, you get outside that sector. So this is the kind of thing that you do. You preserve, you use the point group symmetries to minimize the number of configurations, and you use any conservation laws that your Hamiltonian has to work in a conserved sector. So, and if you don't, you make much more work for yourself. You'll still get the right answer, but you'll get the right answer from double the number of equations. Why do it, right? It's a waste of computer power, etc., etc. So work hard to do that first. So we'll start with L sub 2. We'll then skip L sub 3 because of this, what I've said. So we go up in steps of 2. L sub 2, L sub 4, L sub 6, L sub 8, L sub 10, and I stop when my computing power runs out. And I'll show you when it runs out for this case. If you start with the Néel state or the stripe state and you do L sub 2, just like the problem I did on Wednesday, you've only got one configuration. Just the 2 nearest neighbor sites, and you flip both of those spins. One configuration for either of the model states. For L sub 4, the number's going up now. For the Néel state, you've got 13. For the stripe state, you've got 15. That's bloody hard work to do by hand. L sub 6, it's gone up very considerably. By the time you've got to L sub 10, you're at 500,000 configurations. This number is going up exponentially. That's a shame, but there's nothing I can do about it. That's about, in the case of the computer program that we have written now, and using a reasonable supercomputer, most of our work is done on the one in Minneapolis, the Minnesota Supercomputer Institute, and we can handle regularly about 2 million, up to 2 million is not a problem. Yes. How many lattices? These probably are they. It's probably this one, and this one. I think that's it. But there's more configurations than just this, because you've now got to populate these with all possible ways. You can put 2 in here, you can put 2 in here, or 4 in here, etc., etc. You just have to start doing some counting. That's my approximation scheme. It's not to be questioned. You might have a better one, but this is mine. I don't think there is a better one, but this is mine. And it says at every nth level, I'm going to take these localized set of. Why do I choose them localized? Why do I want these compact lattice animals? Because these Hamiltonians are local. Nearest neighbor and next nearest neighbor. It doesn't seem to make a lot of sense to correlate a spin here with one that's on the moon. Doesn't make sense, or with an infinitely far away on the lattice. That's what you would do if you were doing coupled cluster singles doubles like the quantum chemists or the atomic physicists do. If you were to do that for this, you would be correlating to even 2 pairs of two spins very far apart. And it seems silly to do that from the word go. This is a very local approximation, very local Hamiltonian. It only works over over nearest neighbors and next nearest neighbors. Yeah.
The square, right? But when you consider the tail or the line for dot, then how is the physical implementation of the calculus?
Okay. Let's do. Okay. It's probably I didn't copy this slide. What we do is we have now a universal code that took us a long time to write. And what it does is, and it's universal because you have this trick of starting with a model state, whatever the lattice with all of the spins pointing down, that's your choice of coordinates. Now, what do you have to do? The first step of the program is to calculate all of the lattice animals of size n. Okay, your computer can do that much better than you can. It just starts putting spins next to each other in all possible ways and deriving all of the clusters that do not differ by rotations, reflections, etc., translations. It then populates the wrong spins in all possible ways, so it counts that number of, tells you what these numbers are. You then have to calculate e to the minus s h e to the s. And I showed you how to do that with the simplest case on Wednesday. Now you can imagine when you've got 500,000 of these coefficients, it's not such a trivial job. Actually, it is trivial, but it's incredibly tedious. Again, your computer, you teach it with quantum algebra. It's all homegrown quantum algebra to how to take commutators. You then take the overlap of what you've got there with all of these, where are we? So in here, you've got a whole set of patterns of wrong spins. Here, you've got patterns of a pattern of wrong spins, and you've got to find that pattern everywhere it sits in this guide. That's a pattern matching problem. It's not so easy to do by eye because your eye misses reflections and translations and all this sort of stuff. Your computer doesn't do that. He knows how to do that quite accurately if you've taught him properly how to do it, or her. I don't know how you like to call your computer. That gives you the equations, and then you solve them. And we don't do anything very fancy, which is just direct iteration or Newton-Raphson. That's the steps in the program. The biggest step, the biggest drawback is really memory rather than time. Because you can imagine when you've got 500,000 equations in 500,000 unknowns, and they're not linear, they take a lot of storage. And the storage is actually more complicated than the solution. Okay, but that's technical stuff. Say again? I told you the Néel was the state that was the case when only J1 was acting. That's the state with up, down, all the way along, right back to the, let's go back to the very first transparency, or one of the first. This is the Néel state, this is the striped state. These are the classical states. They're both perfectly good model states. The Néel is likely to work better when J2 is small, and the striped is likely to work better when J2 is big. Or in other words, Néel for small kappa, striped for big kappa. But we'll see. We just use them. Just put it in and see what happens. Okay. And then at the end of the day, we've done this up to the certain level, here up to 10th order, and then we use these extrapolation laws to go to the limit m goes to infinity. And really, that's the only place any approximation is ever made. So you know exactly where your only approximation is. And that's rather crucial because in most other methods, you don't. There's at least 2 places where you make approximations, usually even more. There's a big advantage here. It's the only place. Everything else is exact. The derivation of the equations is exact. The solution is exact up to whatever accuracy you choose. It's only going to this limit. So is everything clear? All right. So we've started the J1, J2 model, and many other people have too. We've used some generalizations of it where we put in an anisotropy. You can put in, for example, let your J1 bonds differ in this direction to this direction. That gives you an extra parameter to play with. You can change in J1 and J2, instead of making this an isotropic Heisenberg, you can call it what's called XXZ. So the XX and the YY are the same strength, but the ZZ you give an extra factor delta. And so when delta is equal to 1, you're back to the original model, or when J1 is equal to J1 primed, you're back to the original model. What we find is that, and I'm not going to show you these results because I want to show you more interesting results. What we obtain from doing a lot of these sorts of calculations, remember, classically, the Néel state exists out to a value kappa equals 1/2. There's then a second order phase transition, energy and its derivative with respect to kappa are continuous, and then it goes over to striped. What happens quantum mechanically for spin half is that the Néel phase exists out to a value slightly smaller than 1/2. The striped state exists for a value somewhat bigger than 1/2. And in between, there's something else. Whatever it is, it ain't classical. It's got no classical counterpart. And that's what makes this problem interesting. Because in this middle paramagnetic phase, it's a paramagnet because it's got no discernible magnetic order. And the question is, what is it? And that's one of the big unknowns. Now, as I say, by now, over the last 30 years or so, there have been many, many studies of this model using a whole slew of theoretical techniques. Density matrix renormalization group flows, variational Monte Carlo, bond operator methods, other tensor network studies. By now, there is a reasonably broad consensus that Néel order persists out to a value of about 0.43, less than a half. Striped order exists for a value above about 0.6, 0.60, and there's something else in between. There is no real consensus, even now, on the nature of the states in the paramagnetic regime, and nor does everybody agree with these two numbers. Even getting these numbers is a real coup. Probably the best of the recent calculations on this model have been done using the CCM and using the DMRG, and both of those, and looking very carefully at those and really trying to be neutral about how good these calculations are, these probably are the best. And they give, they're both compatible with Néel order exists out to about 0.45. It's very interesting. This transition, this first transition from Néel to the paramagnet is not a Landau type transition. Instead, it's a second order deconfined transition. And when we first saw this transition, and it was before Senthill and his Indian, they're all Indian collaborators, right? It's Tadadri, Senthill, and these other guys, Indians in the States, who came up with this idea of a new set of phase transitions, these deconfined. When we first found this, they hadn't done that, and we ran into all sorts of problems with referees who said, you must be wrong because you're in violation with what Landau told us. And I kept saying, well, Landau's not the only guy that Landau transitions, you can get other classes of them. It's quite hard but when you don't have an actual set of, it's hard sometimes to persuade referees, particularly when they're Russian, as I'm sure this nuisance one was. It became much easier once, and we could show this was a second order deconfined transition later. Then for the first bit, it seems that there is a gapless quantum spin liquid. And then in that intermediate range, there are at least two phases, a quantum spin liquid and one that's got a valence bond crystal order, in this case, a plaquette valence bond crystal. So on each of the squares, the four spins are coupled to a spin zero. And that transition, the next one, from striped to the the plaquette valence bond crystal, is a first order transition. Now, while there is quite broad agreement on the value for this second transition, this first one, there's still a lot of room for disbelief. And there are some real outliers from calculations that look pretty good. For example, there's a quite good bond operator approach, which includes up to cubic and quartic interactions beyond harmonic, and that's state of the art in this, that gives a much smaller value, 0.34. My feeling is it's absolutely got to be wrong, because it's in disagreement with everybody else. But having spoken with these guys, it's not obvious why it's wrong. It's uncontrolled approximations for sure, somewhere in that method, but they haven't identified where those are. Even worse, there's a value which is 0.57, and this is this is using tensor networks. This has got to be wrong because it's higher than classical. But again, it's uncontrolled approximation. So you have to be really, really careful what you're doing here. You do not want to do anything that's got uncontrolled approximations, because even in this, these are the simplest bits to get. It's a tough problem. So what's the nature of the phases? Why is there such sensitivity in determining these values? And in particular, what I was interested in was answering this question. And one of the ways you can shed light on that is to try to complicate the problem in the sense of introduce an extra coupling, enlarge your phase space. When you've only got the J1, J2 model, you've only got one parameter, kappa. And so your phase diagram is just a one-dimensional. It's not that interesting. What we're going to do is I'm going to take two of these. And I'm going to put a square lattice bilayer. Here's the guy that we started with. And now I've got two of these layers, and I put them on top of each other so that it's AA stacking is what it's usually called. And between nearest neighbors between the layers, I put a J1 perp. Okay, J1 and J2 I'm going to keep positive because that's the frustration. J1 perp, I'm going to say can be any sign you like. Okay, so now we've got two parameters. J2, ratio J2 upon J1 is kappa, and J1 perp upon J1 is delta. Here it is. Now, the effect of delta is quite interesting because it provides competition without frustration, are the words the experts would use. Why is it not frustrating? Well, classically, it's got no effect whatsoever. It doesn't, whatever you put between the layers doesn't affect what goes on in the layers. So it's classically, this guy has got no effect whatsoever. Quantum mechanically, for sure it does. Because quantum mechanically, if these thick, what's that color? Is it purple? I'm not quite sure what that color is. It's the one that's not red or blue. Perhaps it's brown here. If these thick brown interactions are strong, and let's say J1 perp is positive, you want this guy, they want to form spin singlet dimers. And if these are forming dimers, that for sure as heck is changing what's going on in the plane. That's a purely quantum mechanical effect, got no classical counterpart whatsoever. And if J1 perp is strongly negative, it wants to line up the spins in the across the plane, the interplane, and two spin halves aligned in this as the strength goes up becomes a spin one. So we've got two interesting limits. When J1 perp goes to infinity plus minus infinity, this bilayer, spin half bilayer changes into a spin one monolayer. And when J1 perp goes to minus infinity, you've got these interlayer dimers forming. So it's quite an interesting problem. Okay, so what I'm going to do now is to examine the case, the model state now. I'm going to just put the ground state Nael or the ground state stripe phase on each layer. And now I'm just going to do CCM again. Now the number of configurations goes up, but not dramatically this time. Now, a priori, what do we expect? As delta is turned on from 0, either positive or negative, what you're doing is you are taking a step towards three-dimensionality, right? You're enlarging, you're no longer just in 2 dimensions. Obviously, it's not wholly three-dimensional because you don't have an infinite number of layers, but it's taking a step towards three-dimensionality. And what's very well known in this game is the higher the number of dimensions, the weaker quantum fluctuations become. Not too surprising because infinite number of dimensions is the same as classical. So what we expect, and you'll see this, is that you expect cusps in this case because these guys should extend further than they did for the case where we had the monolayer. And as delta goes to minus infinity, it behaves as a spin one monolayer. And unlike the spin half case, the spin one model shows a direct transition from Nayel to striped. It's not at a half, but it's a value quite close. There's no intermediate phases. So spin 1 is much less interesting than spin half. Again, no real surprise there, because as you go up in spin quantum number, you get more and more classical. All right. And then in the end, we calculate the ground state energy, the order parameters for either of the states. And I can also calculate, I'm not going to talk about it today, I can also calculate excited states, and we can look at the spin gap. I've got results if anyone's really interested, but I'm not going to show those today just because there isn't time. And I'm not going to show results for energy because, as I showed you on Wednesday, energies are not that interesting. It's the order parameter that's interesting. Okay, here we go. On the left, sorry, on this transparency, I'm starting with the Nayel model state. It should work for smaller values of kappa, right? And I'm choosing here a value of 0.3 and a value here of 0.5. And what I'm doing here is plotting as a function of delta. That's the interlayer coupling strength, right? The guy that joins the two monolayers together. L sub 2, L sub 4, L sub 6, L sub 8. This is the extrapolation. And to show you this extrapolation is pretty good, I'm doing two separate, one based on 4, 4, 6, 8, 10, and one based just on 6, 8, 10. And you see they're almost on top of each other. This is pretty robust. At this value, the Nayel state, what you see is for this value of kappa, the Nayel, as we go to larger values of positive values of delta, the order parameter first increases. That's the step towards three-dimensionality. That's the cusp that I was talking about before. But ultimately, it turns over and the order parameter goes to 0 at a particular value of delta. And the same thing happens here, this higher value of kappa. Now you get an even more interesting behavior. You get this gap, and you expect that because I showed you that kappa of 0.5 already has some intermediate states, this intermediate paramagnet. I can do exactly the same thing starting from the striped state. Here I'm choosing two bigger values of kappa because that's where you expect the striped state to come into its own. And you get a similar sort of behavior. I'm putting these guys together now as a family. This is Nayel on the left, striped on the right. Each one of these different color curves is a different value of kappa. So kappa of 0 is where there's no frustration in the plane. That's this red guy. And when delta is equal to 0, that is the pure Heisenberg antiferromagnet with only J1 bonds. And one of the old questions was, probably first asked by people like Phil Anderson, was, are quantum fluctuations strong enough on the square lattice to completely destroy Nayel order? And the answer is no. Nayel order is destroyed partially. It's not if the perfect order would be m is equal to a half, right? It's proportional to s. The order parameter is the average value of the expectation value of the z component of spin, and it can't be bigger than a half. But so it's decreased to about 60%. But now, as you start to increase kappa, so come down here, as you increase kappa, so sticking at delta equals 0, this is the monolayer, right? And what happens is that the Nayel state disappears at a value which is close to this. That was the 0.45 value, but I was telling you where the monolayer, the Nayel disappears. The same thing happens over here for striped, and you get a very similar picture. And what you see is, again, in here, this yellow guy is a 0.6. This red guy is at 0.58. And so that's where the striped order originates. And that's the value of about 0.59 that I was telling you about before. You can do exactly the same thing in putting the two together and looking the other way around now, plotting as a function of kappa for different values of delta. Ultimately, what you want to do is to put all of this together and do a phase diagram. So I take all of those curves and I look where the order parameter disappears, and that's my phase boundary. So delta equals 0 is the monolayer. That's where the Néel order disappears, and it's this value at about 0.45. That's where the striped order appears, and it's about 0.60. As you increase delta a little bit from those values, you get cusps, because that's the step towards three-dimensionality. The order exists a lot more. And so this cusp starts to develop, and this cusp starts to develop. These two guys meet at a triple point. That's no surprise, because when the delta becomes large and negative, that's going in this direction, that's where the two monolayers, the spin half monolayers, merge to become a spin 1 bilayer. And as I told you, the spin 1 monolayer only has a single phase transition between striped and Néel. It's not exactly at a half, but it's close. Up here is much more interesting, because we could have had two things that happened here. We could have had that this cusp, which is emerging here, could have met this cusp and met at a triple point, and then they could have stuck together and then peeled off. They have to peel off because you go to this dimerized state ultimately. This calculation is accurate enough to distinguish between those two. I mean, there's a lot of points in here. And this, you see, it's really an almost classic example of an avoided crossing. It's an avoided crossing type phase diagram. Now, what you see from here is this cusp for the Néel state is incredibly sharp. These guys come in at a very shallow angle. This cusp is not quite as sharp. Well, that's the explanation of why that guy is hard to find. This guy is less hard to find. And that's what we found in just studying the monolayer. You can now explain that by going to the bilayer and understanding it in terms of this. So that's what I say at the bottom. This phase diagram really does explain the extreme sensitivity in these calculations of the monolayer critical points. Please. This is for the bilayer. This is delta, this is kappa. One. Well, you mean like on Wednesday? Yeah, on Wednesday I only had one parameter, right? So I didn't, my phase, like for the case delta equals 0, I've only, the phase, for the J1, J2 on the model, my phase diagram is just a line here, and it's only got 2 points on it. And that was the same for Wednesdays. Yeah. I mean, exactly. I mean, I said this cusp behavior is expected. It's this step towards three-dimensionality. The fact that this branch meets this branch is expected. It's not known. It was not upright beforehand. It was not known where they would meet. And it's not a terribly big value of delta. So where the two bilayers, sorry, the two monolayers become like a spin 1 bilayer is not at delta goes to minus infinity, which is where you really, it occurs at a much smaller value of delta. The only thing we didn't know that was going to happen here was, were they going to meet or were they going to avoid each other? And I can't tell you why one happened or the other. That's the result here. Yes? Yeah. So we're about here. Yeah, that's what I'm saying, right? I mean, what I know here, the blue region is colored so that in the whole blue region, the Néel order parameter is non-zero. It goes to 0 at the edges of this boundary. Over here, or in all of the red region or the pink region, the striped order parameter is non-zero. In the white region, it's not one or the other. And at this point, I can't tell you what it is. I can just tell you it isn't classical. It isn't quasi-classical. Now you have to do another set of calculations to try to determine what it is. And I don't have time to tell you today what those other calculations are. But in conclusion, at this point, what I can say is I don't know of a more powerful or more accurate method for dealing with these strongly correlated and highly frustrated two-dimensional spin lattice models than the CCM. This is one example out of tens or 20, I'm not sure how many. Many models have been done, including these here. Different lattices, triangular lattices, Kagome lattices, hexagonal lattices, etc., with equal sort of accuracy and appeal. Oh no, I should ask, should I stop or should I take another 10 minutes to try to answer why is this method so successful? Take another 10 minutes, okay? So this is Landau's second pearl of wisdom. This is something he would say to his collaborators, and he'd say, look, you've got this outstanding result, but you don't understand it. That's truly shameful. It's not sufficient to understand why something is working. It's not sufficient to know that you've got a methodology or you've got an outstanding result. You've got to understand its meaning. And I'm fully with him there. So given this power of the method, can we try to understand why it's working so well? And I can give you some clues as to that. And one way it may seem arbitrary to do this, but one way to do this is to expand our field, our horizons. So far, we're talking about stationary states. We're talking about, in particular, the ground state. What if we try to broaden our perspective a little bit? What if instead of doing time independent, we do time dependent? So we change from h psi equals e psi to h psi equals ih bar d by dt of psi, time dependent. So you let these coefficients now become time dependent. The parameterization stays exactly the same. Now, what you know is from Mr. Dirac that the thing that plays the role to extremize for the stationary case, where it's the expectation value of the Hamiltonian, is now the action. And here's the action. So it's just sandwiched between psi and psi tilde. It's I d by dt minus h. And it's kind of obvious, right, that the extremizing that with respect to the ket just wipes the ket off and gives you the ground state Schrödinger equation for the bra, and taking off this and now integrating by parts so that the d by dt acts that way gives you this guy. So it's kind of obvious that this is the case. But now insert the CCM parameterizations in here. And now take this time derivative, acting this way is dead easy. It's just e to the s times s dot. So here it is here. And the e to the minus s and the e to the s have cancelled. Right? And although s and s tilde started out looking very asymmetric, now when I've done this, they're looking much more symmetric. They're now both linear. And this is really one of the keys to why this bra state is the right thing to do. It's not just because it satisfies the Hellman-Feynman theorem. There's something deeper behind it. And it's this. And if you just plug this in and insert a complete set of these states in here, you get this. Now, if I extremize this with respect to, let's say, to the s tildes, that's immediately obvious, and I get this set of equations. And if I, first of all, do an integration by parts to get the dot over onto this one, I get a minus sign coming in, and then I extremize with respect to this, and I get these. Well, already these are looking somewhat familiar. This is not a million miles away from Hamilton's equations of motion for a one-body problem. X dot is dh by dp, minus I p dot is dh by dx. So if s, sorry, and they wouldn't have the i's. Sorry, they would be without the i's. X dot is dh by dp, p dot is minus dh by dx. X and p canonically conjugate variables, as Hamilton would call them. Apart from the factor I in here, they're rather similar. Of course, this h bar now is a much more complicated thing than a half p squared upon m plus v of x. That was a one-body problem. This h bar is now a many-body problem, and it's a very complicated functional, non-linear functional of all of these guys and linear in these guys. But once you know it, the equations are pretty simple. What about an expectation value of an arbitrary operator? Well, take V, a time dependent, and plug it in here. Okay, so this V bar, the expectation value of an arbitrary operator, depends on this set of parameters, and t. Just use the chain rule of partial differentiation. So dv bar by dt is curly dv by dt, that's the time dependence that's in here, plus, this is just the chain rule. These guys, dsi by dt and ds tilde I by dt, I can plug in from here. Do it. And you get this, where this curly bracket is defined here. It's defined here. Well, this guy looks just like Hamilton's equation of motion for classical mechanics. It really is identical to Hamilton's equation of motion for classical mechanics, except, of course, this V bar and H bar much, much more complicated. It's no longer a one-body simple problem. It's a many-body problem now. And this guy is nothing more than a generalized Poisson bracket. If you only had X and P, this would be what you would, and that's the standard terminology for a Poisson bracket. It's the curly bracket, and it would just be the Poisson bracket for two C numbers A and B is dA by dx dB by dP minus dA by dP dB by dx. So it's looking Pretty nice, right? I mean, this is stuff that we're familiar with. And it is, in fact, this is the exactly mapped equation of motion. This is what we would have for the Heisenberg equation of motion, and this is what we've mapped it into. And this isn't an approximate mapping. This is an exact mapping. This is an exact mapping of an arbitrary quantum many-body theory onto a classical theory. It's not approximate. It's a classicization of a quantum many-body problem. It's not a trivial classical problem, for sure. But if you knew this guy and this guy, all of the quantum mechanics is incorporated, because by construction it's been incorporated. But on this guy, you do classical mechanics. On this guy, you do quantum mechanics, and you are guaranteed that they are the same. So it's a rather deep result. And it came in because S tilde and S, e to the S for the ket, this strange combination for the bra, but it was vital. And it's the only thing that could happen to get this term cancelling this one and making these on an equal footing. So although you may have thought a priori, this looks so asymmetric, where on earth, why is he doing that? This is the deep reason for doing it. Now you can go on from there. If you want to make this look exactly, say, I'm calling it an exact classicization map from the Hilbert space to a classical phase space, a very complicated phase space spanned by all of these operators, C numbers, Si and Si tilde. If you define phi, read x, as 1 upon root 2, the sum of them, and pi, read p, minus I upon root 2 times the difference of them, then this is what you've got. And if you only have one phi and one pi, x and p, this is exactly the classical Poisson bracket for one variable and its canonical conjugate. These are the Hamilton's equations of motions for the new variables. This is the phase space. And it's what the mathematicians would, in a modern way of doing classical mechanics, the phase space is a symplectic space. And a symplectic space is one that simply has these not commutators, but Poisson brackets. Now, to complete this description, to really convince you that this is real and not just a bit of an artifact, what I also need to show is that the expectation value of an arbitrary commutator between two operators A and B also maps in exactly the same way. Here I've only done it where one of the operators was H. Suppose I have two arbitrary operators, A and B. One of them doesn't have to be H. Well, I can show you the same thing. Now, it's a little bit more complicated, but not much. Let's suppose I take the expectation value of the products. I put a bar over the pair, right? So that by definition is this. Now, to work this out a bit, let's insert between the two, let's insert a unit operator. And we assert a unit operator, I've color-coded it. The brown guys are the unit operator. Right, this sum over I of this bit, by construction, these guys are a complete set of states. And then I've just got e to the s and e to the minus s. So this what I've inserted here is the unit operator. All right, now on this guy, I'm going to replace this term here by, there's two pieces here, e to the minus s, a e to the s, and ci dagger. I'm first going to replace it by its commutator for reasons that you will see in just a second, but that's not correct. I've got to re-add the bit that was not in the commutator. So that's the commutator plus the bit that wasn't there. Now this guy, it's dead easy to see. This term is precisely the derivative, the partial derivative of the expectation value of A with respect to S, And where do we see that? We see that, well, perhaps I write it. A bar by construction is phi, oh, I think this is, will it hold out? E to the minus S, A, E to the S phi. Remember, each of these S's is linear in the CI. S is the sum on I of these coefficients, SI, CI plus. And clearly, if I take, where are we? Oh, I've gone back too far. Sorry. This commutator. And you can see, where does the S tildes appear? Well, they appear in here and in here. This one has the minus sign, this one has the plus sign. And when you just do that first derivative, you get that commutator. So that's why I've written it as a commutator. It is precisely, and this guy, by construction, he's much easier. The only place where S tilde coefficients appear is here. And when you take the derivative with respect to the CI minus, sorry, the SI tilde, you just get left with the CI minus, which is this guy. Oh, I shouldn't touch, should I? So that first term is very nice. And the bit that's left over, I'm just going to work on a little bit more. I'm going to in this place, I'm going to introduce another complete set of states. That's this brown bit. And so the last term, I'm just going to leave like this. So that's the way the expectation value of a product gets mapped. It's got an easy term and then a nasty term. But the nasty term here, which if I just wanted to calculate that, I would have to calculate. But if I'm interested not in just the expectation value of the product, but at the expectation value of a commutator, the thing that you see in here is this guy is completely symmetric between the interchange of A and B. When A and B interchange, this term becomes this term, except for the change I goes to J, but they're dummy indices anyway. So this, when I interchange the order of A and B, this term cancels. And what you see is that this product, this commutator, gets mapped onto a Poisson bracket. Now, the moment you've got that, that's it. This is now classical mechanics. Not trivial classical mechanics, for sure it can't be, because it's got this, it's got, in some sense, it's got everything that, not in some sense, in every sense. It's completely identical to the original quantum problem. But I hope what you see here is that this gives you a flavor of why this method is so deep and why it might be so powerful. It also gives you some ideas of how, with your knowledge, if you have a good and broad and basic fundamental understanding of classical mechanics, how you might use that knowledge to build, for example, some new approximation scheme that you would like to use for your quantum many-body problem. This is hardly been touched. But this is an exact classicization mapping, and in principle, you can go right back to original work done sort of way back at the start of quantum mechanics by people like Wigner and Weil, who introduced these P functions and Q functions and all of this. And you can take it all over. You can take it all over. You can generalize coherent states. You can generalize things like the random phase approximation. You can generalize things like mean field theory, and you can get whole hierarchies of these things. You have things, for example, in classical mechanics like Noether's theorem. You have exactly the same stuff. This is a classical mechanics. All of this information and knowledge you can utilize. And if I let Dow have the last word, he says a method is more important than a discovery, since the right method will lead to new and even more important discoveries. And the hope of showing you something like this is I've given you a method that is worth looking into because it does some extraordinary things at a rather deep and fundamental level. And a lot of it is unexplored still. Let me finish by thanking, in this case, our funders, in particular, the Minnesota Supercomputer Institute, which has funded us for a good time now on for doing these calculations. And again, thank you very much for listening. Yes. Yeah, I mean, sometimes you can be very surprised. You can ask, people sometimes ask, how can it possibly be? Where's the uncertainty principle gone? You know, but it's built in here. It's built in through, and this is known for a long time. People like Wigner and Weil knew this. When Wigner and Weil started looking at the interpretation of quantum mechanics as a statistical theory, I don't mean in usual probabilistic, but as a real statistical theory. And where Wigner introduced this famous P function, right, which is a function, let's say we're dealing with a one-body problem, X and P, one infinite line. And you ask the question, can I come up with a theory? We start with a Schrödinger equation, which is completely symmetric between X and P, right? But what happens is when we quantize and go to a representation, we go either to the X representation or the P representation. That's the canonical way of doing quantum mechanics. But it's not the only way. Wigner asked a long, long time ago, 1920s, right? I mean, 100 years ago, asked the question, is it possible to come up with a function that is a function both of X and P that is the quantum analog of a classical phase space distribution, in other words, a probability? Well, the answer is no, you can't, because that would violate the uncertainty principle. But what he showed was you could come up with this quasi-probability that has all of the aspects of a probability. So in other words, you've got a function, which is a function of X and P. When you integrate over P, you get the X space probability. In other words, psi X modulus squared. When you integrate over X, you get the probability in P space. In other words, psi of P modulus squared. But the function itself has the curious property, not unexpected, but curious property that it's not positive definite. And this was the Wigner P function. And if you don't know that stuff, it's very well worthwhile investing some time in it. And it's another way of doing quantum mechanics. It's very, very well used in quantum optics. So quantum optics people know this stuff inside out. What this stuff that I'm doing here, in some sense, generalizes all of that from a single variable, Q and P, to these multiple variables, the S's and the S tildes, or the phi's and the pi's, which are the sums and differences. And it may be if I make another visit later in the year, it may be that you would like to hear about some of this phase-based stuff, but it would be something else that would that I would gladly talk about, and it's becoming very topical because it's now being picked up hugely in the field of quantum information as well. This work that originated in, as I say, originated 100 years ago by Eugene Wigner and Hermann Weyl, and then got picked up by in the field of quantum optics, where there was the Nobel Prize, perhaps the somewhat controversial Nobel Prize, where the great Indian physicist George Sudarshan did not get a share, but everyone thought he should because of his work in precisely this area. But that's another story. But the deal is that you can do this exact classicization, which gets away from wave functions. That's been known, right? I mean, Wigner and Weyl knew how to do that. They wanted to reformulate quantum mechanics in terms of these other functions that were functions of both x and p, that had within them all of the usual quantum mechanics. And what this is doing is now generalizing that. Yes. Well, as I say, at the moment, this is very much it's very much an open field. Well, oh, thanks. One thing that for sure is just interesting of and by itself is to generalize coupled cluster theory for stationary states to time-dependent phenomena. And I think a lot of people are becoming increasingly interested in that. Again, particularly in the field of quantum information and quantum computation, it becomes very interesting to know how does a state evolve, so we have a framework for doing that, and it's very useful to know that framework can be, and it doesn't have to be, but it can be reinterpreted purely in terms of a classical, a very complicated, but nonetheless a classical field theory. And the sorts of things that you can imagine doing are using your knowledge of classical field theories or classical mechanics, for example, to try to invent different truncation schemes. You know, for example, in quantum chemistry, to get away from this singles, doubles, triples, or from here, getting away from this L sub. I mean, this L sub is already has gone way beyond singles, doubles, but nonetheless, it's got this exponential increase with order, and you'd really like to come up with schemes that don't do that. Nobody has yet. To my knowledge, nobody has yet. But what I'm saying here is this gives you a new perspective. And it may be always what happens is when you reinterpret a piece of physics in a new language, almost always it gives you another way of shining your light onto it and to, well, you know, this is this is state of the art now. And you know, so well, that, yeah, you know, it's up to you now. If you're interested in this, pursue it. You know what's there. Cusp. Yeah, I mean, by a cusp, I simply mean something like this. A point at which this is a curve at which there is a point that the gradient discontinuously changes. That's the mathematical definition or the graph theory definition of a cusp. It's a point on a continuous curve where there is a finite discontinuity in the slope. And of course, you can generalize this to higher dimensions. I mean, it's the kind of thing that these will become folds. It's the kind of thing you get a sheet of paper and you slowly compress or fiddle with it. You just take a sheet of paper and you mess with it. And it stays continuous until you get to the point where you crush it and then you've made a crease in it. This is a one-dimensional analog of a crease. Are we done? You're very welcome.